Okay, let's try. Yeah. Let me know if you can see my slides. Okay, great. So I think we can get started in this case. So, hey everyone. Today we will be kicking off this tutorial session with a talk about geometric deep learning, as the title implies. And to kind of seed this particular discussion, we would probably want to have a bit of a grounding in what is exactly the thing that we mean when we say geometric deep learning? Why might it even be a good idea to think about geometry in the context of machine learning and especially deep learning? And to try to motivate this particular connection, I'm going to kick off this talk by taking you back in time. And when I say back in time, I mean way back in time to about 300 BC, to the days of Euclid. Euclid, as you know, is the inventor of what we know today as Euclidean geometry. And for many, many years, this was the only way to do geometry. So if you were doing geometry, you were basically doing Euclidean geometry, and the foundations of which have been outlined in Euclid's Elements, including various important postulates, such as the parallel postulate, which is given here at the corner of this slide. And for many centuries, people have tried to verify that indeed this is the true way to do geometry by basically trying to assume that this parallel postulate is false and then trying to drive a contradiction. But what actually happened, as you probably know, was that around the 1800s, which were a very exciting time to be studying geometry, various mathematicians have showed that not only do you not arrive at a contradiction, you end up discovering completely new self-consistent geometries. So especially Lobachevsky and Bolyaev were among the first ones to discover this and laid the foundation for what is now known as hyperbolic geometry. And specifically Bolyaev, when he first made this discovery, is infamously quoted as saying he's discovered such wonderful things that he was amazed. Out of nothing, he has created a strange new universe. So there's truly some really exciting stuff potentially hidden in here. And it was further extended through the work of Riemann and the various elliptic geometries that he has proposed. So doubtlessly, the 1800s would have been a very exciting time to study geometry because suddenly there was this explosion of brand new ideas with their own terminologies, their own setups, and so on. And a question that any incoming student of geometry might be asking themselves is, what is the one true geometry? What is the specific assumptions that they should assume to be the most general ones to be used for any problem that they start facing? Well, only a couple of decades were necessary before the first foundations for solving this problem came about. And it came through the work of this mathematician by the name of Felix Klein, who had at this time in the 1870s just been appointed for a professorship at the University of Erlangen in Germany. And his research program that he proposed at the time, which is now commonly known as the Erlangen program, has actually proposed in itself a blueprint that could be used to study all of those geometries under a common lens of invariances and symmetries, formalized using the language of group theory. And this has been one of, in my opinion, the most influential ideas in mathematics in recent centuries, especially because it had massive spillover effects in mathematics and otherwise. So it's very hard to overstate the impact that this program had. Obviously, it helped us unify all the geometries that were around at this time, and this was primarily formalized through the work of Élie Cartan in the 1920s. But beyond that, it had great effects that spilled over to other areas of science. Perhaps the most notable area is physics through the work of Emmy Noether in 1918, which basically showed that all conservation laws in physics can be rediscovered just by appropriately applying a symmetry-based argument. And in fact, similar ideas through irreducible representations are what led us to what we now know as the standard model in physics. That's the classification of elementary particles. And for the computer scientists in the crowd, you might know category theory as a very popular method for reasoning about various aspects of theoretical computer science. And specifically through the words of the founders of category theory, Eilenberg and MacLean, their entire area can be seen as a direct extension of Felix Klein's Erlangen program. So one very simple idea of trying to geometrically unify a bunch of approaches in the area in the 1800s has led through truly amazing spillover effects across all of science. And now you might be wondering, why am I telling you all of this in a tutorial which is fundamentally based around deep learning and graph machine learning, right? Well, specifically, if I take you now to the year of 2020, deep learning is all the rage right now. We have all these different amazing architectures being proposed. And usually with these different amazing architectures, we have different kinds of potentially bombastic statements like, everything can be seen as a special case of a convolution. Everything is a special case of graphs, so you should be using graph neural networks. Transformers use self-attention, and as we know, attention is all you need. And long short-term memory is Turing complete, so why would you ever need anything else? These kinds of statements make it very exciting to be thinking about deep learning, but it also makes one beg the question of, if all of these different architectures are claiming to be the one true architecture, which one is it really? So if history is to teach us anything, at least, the area of deep learning circa 2020 feels a lot similar to the field of geometry around the 1800s. So if history really is to teach us anything, now is the time to look back to the various geometric principles and to try to use them to truly make sense of this zoo of architectures in a more principled manner. And since this is a tutorial on graph representation learning, and I do come from a graph representation learning background myself, you might be asking yourself, could graph neural networks be a possible answer to this question? And you might be right, because if we squint hard enough, many or any neural networks can be seen as message passing over a particular graph structure. And this, here you can see just some examples of the graph structure that might be induced in a fully connected layer, a convolutional layer, and a recurrent layer. So at least intuitively, we might believe that graph neural networks could play a part in this one true architecture. But in order to properly make sense of this, we must be able to understand graph neural networks beyond just the notion of permutation equivariance. And this is what my tutorial is going to be all about. And with that in mind, it is now our turn to study geometry. My name is Petar Veličković. I'm a staff research scientist at DeepMind and an affiliated lecturer at the University of Cambridge. And together with Michael Bronstein, John Bruna, and Taco Cohen, we have set out on a journey to discover exactly these connections, which we have summarized in a 150-page proto book that we put on the archive. You can find a lot more interesting goodies at geometricdeeplearning.com. But now, for the purposes of this talk, let's take you on an interesting geometric journey through the foundations of deep learning. So, for this particular tutorial, we're going to start by just reasserting the case for why we need to plug geometric constraints in our architectures. This is basically because learning in high dimensions is a fundamentally hard problem. And in fact, it's often intractable. As you know from the curse of dimensionality, even under very simple constraints on your target functions, as you scale up the amount of dimensions you're doing the learning in, you suddenly require exponentially many training samples to properly fit that kind of training data. So high dimensional learning is cursed, and low dimensional learning, as we know, often drops a lot of fidelity in the inputs. So how can we deal with this problem? We stay in high dimensional learning, but we try to inject some assumptions about the geometry of the problem through the use of inductive biases. So now we're still doing a high dimensional problem, but we're trying to only work with functions that respect the underlying geometry. And this might make our high dimensional problem more tractable simply because the space of possible solutions is much smaller. And here are a few popular examples of inducing geometry. So in the case of images, you might want to process this image data independently of any shifts. For example, in the case of this cat image over here. For a more exotic domain, if you have data that lives on a sphere, you have the smiley face on a sphere, it is still the same smiley face no matter how I choose to rotate it along the surface of the sphere. So spherical data should in principle be processed independently of rotations. And when it comes to graph representations, which is the area that we're all here to listen to, this data on a graph should be processed independently of any isomorphisms. So here, I've given you two graphs. If you stare at them, you'll see they're exactly the same graph. I've just chosen to present them to you in a different way. And ideally, I should get exactly the same answers when I try to run my neural network on those graphs. So let's try to take these intuitive ideas and try to formalize them a bit more concretely. So first, in order to do that, we're going to need a bit of mathematical background. So we will first define a domain omega, which stores our data. So in the case of images, omega could just be the set of all pixels of the image. And then we endow the different elements of the domain omega with some features from a set C. So basically, we define a signal x as a function that maps individual elements of our domain to the corresponding features that they have. So this set C is usually some real vector space. So in the case of input image data, it will typically be a three-dimensional vector space telling you the red, green, and blue channel dimensions of an image. And then we can define the space of all C-valued signals on omega as this capital X of omega C. It's just a set containing all those possible signal functions we can have. And what's very convenient for us, because deep learning often rests on linear algebra, because often our domains in computers will be discrete, we can represent these signals not as functions, but as matrices, capital boldface X, which is just a real matrix with the number of rows equal to the number of items in the domain and the number of columns equal to the dimensionality of our feature space. So the ith row of this matrix will give you the features of the ith node of the domain. Okay. Now, once you have this kind of structure of signals, you can then impose some interesting properties on it. And typically, you'll want them to support these linear combinations in a natural way. So if I take any linear combination of two signals, it is the same as first looking up the signals in each of the two parts and then linearly combining them. And this means that the space of signals forms a vector space. And often we can also define an inner product on these spaces, which can be very useful, where we just basically integrate over all possible pointwise dot products at every possible point of the domain. And these two conditions taken together mean that our space of signals is just a Hilbert space. Now we can start talking a little bit about symmetries. So before I zoom in on what do I mean by a symmetry of an object, if you think about it, it's basically a transformation that you apply to an object and it doesn't change the underlying object. So we might look at it in a different way, but it's still the same object. Now, one very important point here is that just the very act of me saying that this is what a symmetry is imposes some properties mathematically that a symmetry must have. And in this particular case, just to show you an illustrative example, imagine that my domain are these triangles, and I'm storing data in the three corners of a triangle. So some possible symmetries I could apply to that triangle are rotations and horizontal flips. And here you can see exactly all the possible ways in which I can present this same triangle, depending on the way I choose to rotate it or flip it, and the various connections between those transformations. So the R's and the F's are the symmetries of this particular triangle. And as I said, because a symmetry is a transformation that leaves the object unchanged, this immediately defines a few properties that it must have. We must have an identity transformation, and it must be a symmetry because it trivially doesn't change the object. If we have two symmetry transformations, we can always compose them and get a symmetry as a result. And also symmetries must be invertible, because if I cannot invert the function that I just did, I've lost some information. And as a result, the object hasn't been unchanged. And further, the inverse must also be a symmetry itself. When you combine all these axioms together, in fact, you recover a very standard and well-appreciated object in mathematics, which is the group. And here I've just listed out the various properties that group transformations must satisfy. So we have a set G, which contains all of those transformations that we care about, and some binary operation GH, which is basically a composition of the two operations. And that composition must satisfy the following properties. So it must be associative. So if we have three transformations applied in a particular order, it doesn't matter how we choose to pairwise compose them, we'll get the same result. there must exist an identity which satisfies the obvious properties, there must exist an inverse which satisfies the obvious properties, and there must be a closure property. So whenever we have two elements of a symmetry group, composing them will also be part of the symmetry group. On the right-hand side, I've shown another case of a very interesting symmetry group, which is actually rotational symmetries of a Rubik's cube, the group O of H. So basically, the symmetry group in our case is just a group of some transformations G that take points on the domain and move them somewhere else in the domain. And the group operation will just be a composition. But when we talk about groups more abstractly, there's just a set of elements with some composition rule which satisfies these axioms. So to properly be able to work with groups, we have to tell something about how the group operation acts on data. So we can define the so-called group action, which takes a symmetry group element G and a domain element from omega and tells you where that particular element ends up, such that some obvious properties are satisfied. So there's associativity with the group action, and also identity applied to any point on the domain leaves it unchanged. And here's one particular example of what a group action might look like on Euclidean planar motions. So here you rotate by some value and you translate by some vector. You can always create some kind of an action matrix, as you know from computer graphics, which can be applied on the coordinates to transform them in this particular two-dimensional space appropriately. And once you have an action of a symmetry group on the domain, we can also automatically obtain an action of it on the signals. So I can apply my symmetry transformation not only over omega, but also over signals over omega. So G of X, where X is some signal, is the same as looking up X on the point that will end up at U after applying G. So it's X of G to the -1 of U. Why is this the case? So when I apply G to G to the -1U, I'll get U as a result, and that's where I want to look up X. And here is it visualized on the case of rotating a sphere and then a point ending up in a particular place after applying a rotation transformation G. And further, we will almost always assume that this group action is a linear operation, such that if I have a linear combination of two signals, like these two insects superimposed together on an image, it doesn't matter if I first add the signals together and then apply a shift, or if I individually shift the two signals and then superimpose them together, I'll get exactly the same outcome. And why is this convenient for us? It's convenient because then I can define a representation of my group action in a way that completely stays within the realms of linear algebra. And this is obviously going to be very useful for deep learning because we reason about most of deep learning in the lens of linear algebra. So we say that the n-dimensional representation of a group is a map rho, which takes elements from the symmetry group G and gives you a unique n by n invertible matrix, which satisfies the operations of the group and satisfies the required associativity laws. And here's one specific example of how a group action might look like for cyclical shifts of a particular one-dimensional signal. It basically gives rise to the usual shift matrix just raised to a particular power. And now with this notion, since we have a linear algebra definition of a group actions, now I can talk about what it means for my function to respect these symmetries in G. So first, if we expect that the output of our problem does not depend on the symmetries of the data, we can talk about G invariant functions, such that, so these functions or these neural networks F are such that no matter what symmetry operation I use rho of G to represent its matrix representation. If I apply it to the input, I'll get exactly the same output, regardless of whether or not I applied it. And this can be reasoned about in the case of image classification, for example, where your output class should not in principle depend on shifts of the image. So this is the property that usually a convolutional neural network might encode. However, sometimes, so this invariant prediction gives you one prediction over the entire domain, so one class over the whole image. But sometimes you might be interested in making predictions over individual elements of the domain. So in the case of images, this might correspond to segmentation, where you might be predicting a segmentation mask, and every prediction in every pixel must follow any shifts in the input in this case. So we need a more fine-grained notion of G equivariance, which is for every group action G, it doesn't matter if I apply it before or after applying my function f, I'll still get exactly the same result. So in the case of segmentation, what does this mean? If I translate my input image, I will not get exactly the same segmentation mask, but rather it will change in a predictable way. It will shift in exactly the same way that I shifted the input. Now, these two properties in and of itself are not enough usually to ensure scalable and stable learning. And in fact, usually we want an extra constraint, which is we want our signal to be stable under slight deformations of the domain. So we might have a particular input image like this, and we might build our convolutional neural networks to be resistant to shifts, but nature is usually not quite as ideal as this. So it might shift our image, but it might also distort our house a little bit. And a CNN is not by default designed to deal with these kinds of distortions, but we can actually mathematically derive what might be meaningful properties of a neural network layer to be able to deal with these errors so that they don't immediately propagate everywhere in the input. And the conclusion in this case is that rather than doing global layers, the layers should be local on the domain and only deal with local neighborhoods of a particular domain input. So that's why CNNs are usually constructed with very small convolutions, like 3x3 kernels, but make them very, very deep to stack the effects. And using all of these different ideas together, invariance, equivariance, and locality, we arrive at the key building blocks of geometric deep learning, where we have equivariant local layers and invariant layers, as we discussed before, if they're necessary. The reason why we're happy with these equivariant layers just being linear is because in deep learning, we typically inject nonlinearity by just a pointwise activation function, which is applied to every part of our signal separately. And there are many universality results that show that if you combine linear equivariant layers with just pointwise activation functions, you get universal approximation properties over these domains. So there's no need to do anything more complicated than this. Sorry, was there a comment? Okay. And the last part, which is sometimes important, especially when you deal with images, is this local pooling or coarsening layer, where we sometimes go over inputs of a particular domain to try to coarsen them on some smaller domain omega prime. This is very useful for images, not that useful for graphs in recent times, so that's why we don't talk about it as much in our write-up. And all these components taken together can actually form the basis of this blueprint of geometric deep learning. So you stack equivariant layers, you add some nonlinearities in between, you pool occasionally if necessary, and finally, if you need a prediction over the whole domain rather than individual nodes, you add an invariant layer at the end. And these taken together actually are expressive enough to derive any architecture that you might want to deal with over various kinds of data. And in our book, we show that basically all the fan favorites are derivable by choosing the right kind of domain, the right kind of symmetry group, and working out the maths from there and figuring out how they do this. In the book, we provide examples for various characteristic domains. I will use the remainder of this tutorial, the time that I have, just to show you how this works in the example of graphs. So first, before we start learning on graphs, we are going to have a more simplified learning setup. We're going to look at learning over sets, which are basically graphs with no edges. And in this case, we just have nodes and we have features of the nodes because we usually deal with features in deep learning. So xi is a k-dimensional vector representation of the features of node I. You can then stack these features. That's what we typically do in representation learning into a node feature matrix, where the number of rows is the number of objects and the number of columns is the number of dimensions of the features. So the ith row corresponds to the features of the ith object. Now, the very act of stacking these features into a matrix is bad because it specifies the node ordering, and we assumed our set is unordered. So we'd like the result of any neural network applied to this to not depend on the order. So what we want really is this interesting permutation invariance property where no matter how I present to you the different elements in the set, I should still get exactly the same response. And it will be useful when we define this rule to think about operators that can change the node order. And as you know from combinatorics, these operations are known as permutations. For a set of n elements, there's n factorial many of them. And conveniently, we can use the idea of representations of a group action to note how each permutation defines a unique node-by-node matrix, which that has exactly the desired effect, the so-called permutation matrix. Here you have a specific permutation matrix for the permutation 2413, and the only effect it has is that when you left multiply it with a feature matrix of nodes, it just permutes the order of those nodes and does nothing else. So it's ideal for what we want to show. So now, directly applying our ideas, we can actually derive that a very generic architecture called deep sets is a very concrete example of a permutation invariant architecture over sets that has an equivariant layer applied to every node in isolation. Here in sets, the only notion of locality we have is the node itself, so that's what we use. And then at the end, we apply some aggregation, permutation invariant aggregation if we need to predict stuff on the level of the whole sets. And this is typically as far as we can get with sets without assuming or inferring additional structure. And the applicability of such models is quite apparent in computer vision. Point nets, which were concurrent to deep sets, basically derived many of these kinds of ideas and showed that they work really well on point cloud problems. Now we augment the set of nodes with some edges between them. So we consider graphs, G, which are a tuple of not just nodes, but also edges. We typically represent these edges in many ways, but for the case of linear algebra, I'll just use a slightly inefficient representation, which is the adjacency matrix. So it's a matrix of nodes by nodes, where each element is either 0 or 1, depending on whether that pair of nodes is connected with an edge. And we can add more things like edge features and so on, but I'm ignoring them just for the sake of keeping the maths less tedious, and the findings are largely the same. And the desiderata over graphs are the same as the ones over sets, permutation invariance and equivariance. So what's changed really? If this was the desirable property for learning over sets, for learning over graphs, it's exactly the same desirable property. It's just that now I have edges that I have to carry around and be mindful of. So I can extend the ideas of invariance and equivariance from sets to graphs by just basically adding adjacency matrix as part of the input. And whenever I apply permutation to the features, I need to also apply permutations to the rows and columns of the adjacency, which ends up PAP transposed. So we get permutation invariance over graphs as no matter what permutation matrix P I choose, if I apply it to the features and the adjacency, I'll get exactly the same result. And equivariance, no matter what permutation matrix I choose, it doesn't matter if I permute the features before or after applying my function. Now, one thing that's exciting about graphs, and you don't get it in sets, are these idea of neighborhoods. So on sets, there was no real neighborhoods, every node for itself, really. Here, we suddenly have a broader context. Each node has a neighborhood, Ni, of all the nodes directly related to it. And using those neighbors, we can extract neighborhood features, which I call X and I. It's just the multiset of all the node features adjacent to a particular node. And now our local function doesn't just have to look at one node, it can also look at the whole neighborhood features around that particular node. And we can then apply this function in a distributed manner on all the neighborhoods of a graph, and basically stack the results in an updated node feature matrix. And so long as this function is invariant to the order of the neighbors, the whole function will be equivariant to across the graph permutation symmetry. And it's a fun exercise to prove this. It's just a simple algebraic manipulation. Now, I've derived all of this math to be able to show you this. So what we've been setting ourselves up for is this basic recipe for graph neural networks, and we build them as basically a shared application of a permutation invariant function phi over a node and its immediate neighborhood set of features, and then just applied in a direct way to all neighborhoods separately. And once you have a model like this, you can have a graph input of some node features and adjacency structure, and applying your graph neural network, you update your node features to some values hi. The adjacency typically doesn't change, but there are very exciting methods recently that also try to change that. And once you have these latents, what can you do? You can directly classify the nodes by learning a node classifier over the h's. You can also classify entire graphs, but much like what we did with deep sets, you have to somehow compress all the node vectors into one latent in a way that doesn't depend on the order. And typically summing them or averaging the features is a good way to do that before you pass them through a classifier. And on graphs, you also have this another exciting modality, which is the edges. And you can predict properties of edges or even predict existence of edges, which is a task typically known as link prediction, as just some classifier over the features of the corresponding nodes and maybe some edge features between them if you have them. And I haven't told you much about how to actually implement this local function around the node and its immediate neighborhood. And I don't have enough space in this tutorial for that, but I'll just highlight that there exist 3 possible flavors of GNN layers: convolutional, attentional, and message passing, which from left to right are less to more expressive at the expense of being less scalable and potentially prone to overfitting. So basically, these are the 3 main flavors: the convolutional, where you just compute a simple weighted sum with fixed coefficients over your neighbors; attentional, where you use attention mechanisms to compute these intermediate coefficients and aggregate based on them; and message passing, where the sender and the receiver node collaborate to compute an entire vector, message vector, to be sent across and aggregated in the receiver. And before I conclude the tutorial, well, this part of the tutorial, I'd just like to make a brief note on transformers. So if I take this rule for the attentional GNN and I make my neighborhoods the entire set of nodes, so it's a fully connected graph, I actually recover exactly the equation of the transformer. So I have this attention mechanism over all pairs, and I use these computed attention coefficients to aggregate my neighbors. So using a fully connected graph with an attentional flavor, we can actually make the connection that transformers are graph neural networks. And the only way in which transformers get specialized as sequence models is by injecting these positional embeddings. If you drop them, you end up with a fully connected graph attention net. And these pre-computed features, they give hints to the model as to where you are in a sequence, but the model is not at all required to use them. The main symmetry of a transformer is permutation equivariance. And you can think of this attention matrix as basically inferring some soft adjacency and therefore letting the graph neural network choose its own edges. For a much more interesting and deeper discussion of this, I invite you to check out Chaitanya Joshi's review in The Gradient under the name Transformers or Graph Neural Networks. And I think this is basically where I would like to stop. I had some more material planned, but basically it is about as much time as I think have been allocated for this. So just to briefly recap what we covered, we looked at the geometric foundations of graph neural networks, invariance and equivariance, the symmetry group actions, deep sets, graph nets is a special case for learning over graphs, transformers as a special case of fully connected attention GNNs, and parts which we didn't cover here, but you can definitely expect to find them in the book: composing symmetries over geometric graphs and learning over manifolds and meshes. Last point I'll make is that we have a book and an accompanying lecture course all available on geometricdeeplearning.com free of charge. And we're actively trying to improve all these materials. We recently got accepted by MIT Press for a 2023 release of our book. So any and all feedback will be very much welcome. Thank you so much. And thanks again to the organizers for the opportunity to present at this great event. Thank you.